Welcome back to the channel. So those of you regular viewers will know this is normally a machining and an engineering type channel, but you'll also know that we've recently had this solar panel system installed and it's been really good. One of the problems though is if you've got a hybrid inverter like we have here, then the panels and the battery both go into there and they're both DC. And with a third-party app like Myenergi, you can't see what's going on there. All you can see, you can put a regular CT clamp like this around the exit to the inverter, and then you can just see the combination, but you can't see in detail, like is it charging the battery, is it discharging the battery, we've got loads of sun power, you just can't see any of that. Until today, I managed to find out a way to get this thing to work. I made some custom-made clamps and a control system, and we got it hooked up to the Harvi, and we can now do things like this. So using the Myenergi system, we can now see what's coming into and going out of the battery, the DC part of that, and we can also see what the panels are doing. How did we do that? Well, it's a very long story. Let's get started. Okay, so let's go over a few basics before we get into the video proper. First of all, if you want to measure DC with a CT clamp like this, they don't work. Yeah, this needs a change in current, so it picks up that changing magnetic field and that gets induced in here, and there's a coil on the back and then it sends out a signal out here, but it has to be AC. So you can pick up the AC out of the inverter, but obviously the panels and the battery are both DC. And if you put one of these on there, you'll get absolutely nothing out. But clearly, I've managed to get it to work, and obviously I think you can see the key ingredient, the magic, is here, and the way I've got that control box hooked up. So yeah, it's been a very, very long journey. I would say probably 3 months in development, design and development, probably over 100 hours invested in this, probably spent about £200 on parts, most of which I didn't end up using, as is the way when you're doing research and developing a new piece of equipment. But finally, as you can hear the relays clicking away there, that's the battery. It's charging the battery up at the moment, or going in and out of charge. So apologies for that. Yeah, it's been quite a journey. I'm not an electronics expert, so it's taken me probably twice as long as it would someone who knows what they're doing. But we have got a system that works. So we've got our DC clamps here, and they're feeding into that control system. I've got a custom controller, written some code, we've got some custom electronics. I even had a board made over at JLC PCB, I think it was, not sponsoring the channel, I just used their services. And we made that board. I had to teach myself along the way how to use easy EDA, so I trained myself up in a week, got the board made, sent off, fabbed, sent back, and luckily it did work, so that's great. Yeah, so it's been, as you can tell, an awfully long journey, 3 months of development. So I'm going to split this video up into multiple parts, so you won't see this just yet. You'll have to, if you just want to see the end and just want to see like how I made the last part and hooking it all up, then just wait till the final episode. Yeah, you can just skip past these intro. But if you want to see the journey I've been on, teaching myself all about op amps, the positive and negative rails that you need for those, voltage regulators, stabilizers, oh goodness, you know, how to make custom DC clamps that are actually going to work, how to calibrate the whole thing, how the Harvi system works, because there's no published information about exactly the signal it needs, so I had to dive in deep with this oscilloscope and try and sort of reverse engineer some of it, because it needs a custom signal to work. Yeah, so if you want to follow along, then let's get started. And if you just want to see the end, then by all means wait till the last video comes out and just look at the end. Right, let's get going. Now you might be asking yourself, what's the problem? Because in the Fox app you can see what we've got, 600 watts coming out the panels, and then there's about 300 watts going into the battery charging it up. Yeah, that's great. The trouble is it takes about 5 minutes to update, so it's not really very instantaneous. Whereas the Myenergi app is about every few seconds. So what can you do then? Well, this 254 watts that's coming out the inverter, that's AC, and that is the bit that you can see on the Myenergi app. So you can see, actually that's the 0.2 kilowatts down there in the bottom corner. So you can see that, but in the Myenergi app, which updates every few seconds, which is great, you can't see the DC battery and panels. That is until now, and this special project. Okay, so the clamps arrived, and they are rated 50 amp per 1 volt, so 50 amps of current through there, of AC current is 1 volt coming out here, Now these have got the burden resistor in that enables them to output voltages, which I think is probably the better type for us, for what we want to do here. Now if you're getting these clamps and they're going straight into a Harvi, they need to be have a millivolts of output and have no burden resistor, because you want to put current into the Harvi amp. But in terms of what we're trying to do, I think we'll go with the voltage output, and then we need to process that signal and convert it back into a current so we can go into the Harvi, and then we can calibrate it. But essentially I think that's what I'm going to start with. So just to understand exactly how these are behaving, I've got another one set up over there and a few bits of instrumentation, so let me take you through what I've got. So obviously the inverter's running as, I don't know if you can see that, but there's a variable amount of power going from when the clouds come over, about 600 watts, and then when the clouds clear, 3.5 kilowatts. So we're just monitoring that, and then I've been writing down the wattages there and various signals down here to just make sure I understand what's going on. And then down here you might just about be able to see that, the black clamp down there, that's the original CT clamp that looks at the output that's coming out of the whole inverter, the AC output. The clamp we're testing is the blue one, so basically they're on the same live cable, measuring in the same sense. And then on the neutral there I've got an ammeter, well, it's a clamp type ammeter measuring the current, the AC current. Now it's on the neutral, it's going the other way, but this doesn't care, it'll just give you the positive value. I just couldn't get all three on the same live. So we're measuring the current coming out, and that's measuring the current using this system here. And what it is we need to work out is how to get one to equal the other. So the output of this I've also got teed into this multimeter, so we're measuring the AC RMS voltage, so at the moment 0.05, so 55 millivolts. And then we've also got this going into the oscilloscope, so we can see the sine wave that's coming out of that AC inverter there. So the oscilloscope's down there, that's taking the signals coming out of that CT clamp, and you can see it's quite low at the moment. It might be a little bit out of range, but the current is very low, so the wattage is very low, so slightly less worried about that. I really want to cover the full range and give an accurate reading across most of the range, the mid to upper part. And then down here it comes with this little jack lead on the end of the CT clamp, so I've got part of it going into the scope, a few other clamps there that give me the RMS reading on the multimeter. So we're measuring all those parameters at the same time and just make sure it all makes sense. So what you can see down here, I've been recording all the different values. So this is the kilowatts coming out of the main unit on the front panel of the inverter. So we trust that, and they've got various readings here. You can see when the clouds went over, dropped from 3 to 0.3 kilowatts, 0.6, 1.5. I was trying to pick anything that had lots of differences, so when it changed by quite a lot, I tried to write the numbers down. Now obviously I'm writing numbers down and it's changing sometimes quite quickly. Now I'm to write the numbers down across the different sensors. And it might have changed by the time I wrote the last value down, so it could be a little bit out, but we're just getting a rough idea. So what we got here, so we got, this is the peak to peak value from the CT clamp, which is 50 amp for 1 volt output, and then the RMS, that was the peak on this oscilloscope. Then the RMS measured with the multimeter is here, which is basically the positive bit of that, and then the RMS of that, so it'll be 0.707 of the positive bit above 0 for that signal there. And then here, this is, we'll come back to this in a minute, and then the clamp that goes around the neutral in my case, though it's same as the live, it's just the other sense, but it doesn't care. This is the amount of current it was recording, and then I went into the system and just checked what the grid voltage was it was putting out. It's a little bit high, but it's 246. So if you multiply that clamp amps by the volts, you get these values down here in kilowatts. And if you look here, so we've got 3.2 compares to the front panel showing 3.3, 3.143, 0.37, 0.36, 0.7, 0.6, 1.2, 1.5. So given there's a bit of a delay in me writing them down, it suggests that the current that's coming out that I'm measuring on the clamp is giving me about the right kind of level in terms of what the kilowatts are that agrees with the unit. But more importantly than that, we need to have this column here. So imagine this implementation in the future, all you're going to have is this RMS voltage output from the CT clamp. So you'll just have this signal here, and what I was just checking here was, could I back calculate or work out what the current would be, and the answer is yes. So if you take this number here, multiply, where have we got the value? Yeah, so it's 50 volts is 1 amp, so scale it up by that amount, 50 times 0.2 gets you to 14.5 amps calculated, and then measured with the clamp is 13.3, So we've got 13.3, 12.8, 1.55, 1.5, 3, 2.99, 5, 4.88. So that's great. So from the voltage from the CT clamp, I can work out what the current is, because I'll just multiply by 50 or scale it by 50 in software or whatever I'm going to do, or if it's hardware. And then I know if that with that current there, I know the grid voltage is going to be somewhere between 230, 240, and I know the current that's coming out there. So in this way I'm able to convert. I'm showing this with AC at the moment, but the idea is I want to do it with DC, do the same thing. So this was just to check that the CT clamp that I've just bought is working in the way that I thought it was, and the answer is yes, it makes sense. Okay, now I've got a different type of split clamp here. So this one's got no burden resistor in it at all, so it's rated at 100 amps, is 33.33 milliamps out. So 100 amps going through the main cable through there, that gets converted into 33 milliamps coming out of the cable through here. Now you've got to be careful, because if you clamp this around the cable and there's nothing on the other end there, in theory this would try and go up to a very high voltage because there's no resistor across it. So I don't know if you get electric shock off it, but I'm not going to try it. So make sure this is into something, into your test piece, into the Harvi if you're using that or whatever, before you connect this type. Otherwise maybe you get shock, I'm not sure, maybe someone in the comments would know, but it feels like a pretty bad thing to do. Right, so let's work out the characteristics of this in terms of how this goes into the Harvi, kind of current range, peak voltage if that's critical, I'm not sure, but I'm guessing it just only cares about the current. And obviously we've got to watch out how we do this and try and get a correct signal. So let's set this up. Okay, so we've got the other type of CT clamp here. This is without a burden resistor, so it will just put a current out here. So for 100 amps going through the main cable there, that's the brown live cable, you'll get 33 milliamps coming out of the detector cable. And that's because I think in the Harvi it needs to self-power, and so that current charges up a capacitor and it enables it to generate its own power that way. And then it must have its own burden resistor in there, which it works out, you know, the value of the current that's coming through here. So down here you can see that's the CT cable there, the plus and minus, and then I've got this is set up in amps mode, so it's actually the current's passing through the meter and out the other side. So just note that the little resistor here is just a way to get a metal connector in there, so it's not actually in the circuit. So we're measuring current through the circuit, through the ammeter for that one, and then with this scope we're measuring across, we're measuring the voltage. I wanted to see what the peak-to-peak voltage it needed to run across those. I've got a bit of an output on the scope there, and you'll notice, well, first of all, it sort of pulses on and off. Now that might be because we're right at the limits of the detection, so we're quite low. This is measuring milliamps now. I'm just looking across at the Fox. Yeah, we're putting 0.6 kilowatts out on the main panel, so it's pretty overcast now, pretty cloudy. So it might be because we're at the low end of the specification, and the Harvi's struggling a little bit maybe to do something with that. Okay, that might be a limitation of just this system, I don't know. So what I've been doing then is writing down some values when the current was higher over about the last 20 minutes or so as the clouds come and go, and I'll show you that in the book down here. So what I'm recording down here, this is the clamp. So if I use this clamp meter set onto AC around the live cable, I can measure off the AC amps on there. And I've been doing that down there, so we've got 1.8, 13 and so on and so on. So some big values, high values and medium values. And then I had a look at the Fox front panel on the inverter, the amps it thought was coming out of there, and you can see, yeah, generally they agree within reason. Yeah, we're just trying to get a rough idea here. So the clamp agrees with the Fox, so that's great. And then also on the front panel, if you look at the kilowatts that's coming out at that point, they're down here in kilowatts, so 0.4, quite low, 3.3 quite high. I didn't manage to catch that one. I guess quite low is going to be the answer. 3.6, 0.6 and 0.5. So we've got a range of kilowatts displayed on the front panel, and then the app on the phone, the Myenergi app on the phone, shows you this value here. And so it's kind of close, you know, 2.8 is 3.3, 0.3 is 0.4. It's generally down a bit, but it's close-ish. So that kind of all makes sense. And then the key thing is, okay, for that level of kilowatts showed on the app, how many milliamps are we seeing? And that's what I was looking at the voltmeter in amp meter mode, and those values are down here. And so when we were pulling 2.8 kilowatts, on the app, or 3.3 on the front panel, whichever one you want to kind of believe. I guess this one maybe. We were at 3 milliamps, jumped around a little bit, and I think we know why, because of the signal. I didn't catch that one here, but it must have been pretty low, and it was nearly off the scale, so that's pretty low. 3.6 was around 3.4 milliamps, 0.6 kilowatts, that should be kilowatts, shouldn't it? 0.6 kilowatts was around 0.66 amps, and 0.5 kilowatts, 0.59 amps. So basically, the kilowatts that's coming out of the inverter was related pretty directly to the milliamps coming out here. So 1 milliamp coming out and detected on the CT as a current is about 1 kilowatt coming out of the inverter. So that's one piece of information. Then the other piece is, according to the scope, it's 11.6 volts peak to peak, so I guess it's probably supposed to be kind of 12 volts peak to peak in the way it works. I guess that's fixed, and then the current is changing, and the current changes. I'd have to get that volts, wouldn't? Yeah, actually that volts has been about the same all the way through. So the current's changing, and the current moves up and down in line with the wattage coming out of the unit. So I've got a bit of a calibration how it's all working, and so essentially we need our DC clamp to emulate this number of milliwatts coming out as a sine wave, about 12 volts peak to peak, calibrated so that that many milliamps gives that many kilowatts on the app, and then we've got DC clamp. Alright, that's another piece of the puzzle. Interesting. So I think the sun's come out, and the battery, the house battery, is completely charged. So what can you see on here? So this is saying we've got 2.8. This is my dummy kind of the CT clamp I got loaded on there. I'll just set it up in the Myenergi app, the Myenergi on my Zappi, to say that CT. Let's see what it was. CT1 on my Harvi is an energy storage device, a battery. So this is fake, this is actually around the output of the inverter, but I'm just trying to figure out how it's going to work. So it's got 2.8 kilowatts coming out of there, and we've got, it jumps around a bit, but 2.8 you could say milliamps on the ammeter, and then on the scope, so we're still 14 volts peak to peak, so it's probably a nominal 12. And again, so if I zoom, change the time base on it, let's come all the way out. So I don't know if that's the way it operates, but it's still pulsing on and off. And when I looked in closely, it looks like the peak of that kind of just sort of builds up and then drops and builds up and drops. So maybe that's the capacitor in there working. But whatever it is, I guess it accounts for time on and time off when it works out the whole signal. So it doesn't actually matter as long as it realizes that's something that it does all the time. Otherwise, although I guess it's, I don't know, it's measuring the current, isn't it? So maybe it doesn't matter. Anyway, so that's what we've got. Oh, weirdly, that's just dropped. So that's dropped to point. Oh, okay, and then that's caught up. All right, interesting. So this is almost real time. It's maybe about 2 or 3 seconds behind. So let's see if the sun comes out. Actually, no, the duty cycle's come on longer. I don't know. I guess it's the capacitor, but I don't know the significance of the stop-start there. Anyway, main thing is we're definitely linking kilowatts there with milliamps there, no doubt about that. So I've got a pretty good idea about how we need to kind of fool it to create the signal to make it think we've got kilowatts of AC. Good stuff. All right, progress. Okay, I've been messing around with a few circuits for a while now, and after quite a few hours playing with this, I finally got it to work. So I did start off with this. This is a commercial, something I had ages ago for the go-kart project, for those of you who follow the channel. So I've got a Hall effect sensor here, and when a magnet comes close to it, like this one, the idea is it's supposed to put a voltage out here. I've either got analog or digital out, and then we've got a trim pot there to vary it. I couldn't get anything out of this, so I don't know if it's derived faulty. I did notice one of the solder joints didn't look very good, so possibly that wasn't working. So had a little look around on the internet for some kind of way to do this using an op amp, and didn't take long to find a circuit. So basically that's what I've got knocked up here, and it's essentially this circuit here. Now originally I wasn't planning to do this to give us a voltage divider, so that I could go plus and minus, because I was just going to use it on the panels because they only go one way. But I guess to make this more universal, I'll put the voltage divider in so that it can ultimately show current going in or out. Then you could use it on the battery, let's say. The only one thing to say on this is so this is the Hall effect sensor here. It's going to detect the magnetic field. That got really hot and I couldn't figure it out, and basically the internet was wrong. So this signal pin 2 should have actually been the ground. I looked up the data sheet for the 49E Hall effect sensor that I'm using, and yeah, these were the wrong way around. So I swapped out for a new one, got quite a few of them, and it's now working. And then I had to set these. One of them's like a 0 offset and the other one's a gain, but because I'm using these trim pots on that, I had to find the sweet spot where they were going to work, because outside that range the whole system didn't work at all. So I got it dialed in and it's working okay, and I'm just sensing the output over here. I haven't got the voltage divider in yet, so it's just what you naturally get out of Hall effect sensors. They have a bit of a bias, a couple of volts, and then they'll kind of go up or down from there. So anyway, it's a start. So let me show you what we got and how it works so far. Okay, so I've got a 9 volt supply going in there, and then I've got a voltage regulator that drops that down to 5 because the Hall effect sensor needs 5 volts, but the operational amplifier chip that I'm using needs 9 volts, and then the voltage divider will be run from 9 volts as well. So we've got 9 and 5. The 2 LEDs, you can just about see there. One's telling me I've definitely got a 9 volt supply, and the other one's linked to the 5 volt, so it's a little bit dimmer, but I've definitely got power going in. And then I've got this 1 mega ohm resistor which comes out here. That'll have a decoupling capacitor across it ultimately, but at the moment I'm just reading the leg that comes out, so before the resistor, into the scope, and then we've got that grounded relative to the power supply. So it'll only go, it won't go negative, it'll just do the sense that the Hall effect naturally does. So the idea is when I bring a magnet close, we should see something move on this oscilloscope. Okay, so our little Hall effect sensor's there. The great thing about that is when you bring a magnet close to it or away, it gives you a steady DC offset on here. So a fixed magnetic field gives you a certain level of voltage out here. And the great thing about that is that when we get a DC wire running through our CT clamp, or our modified CT clamp, and that's obviously a static DC, that'll generate a magnetic field still, a bit like an electromagnet still operates. You put a coil of wire on DC, you'll still get a magnet. And the level of magnetism there, inducing that current in there, should induce something in the Hall effect sensor, and that will give us an output proportional to the strength of that field, which is proportional to the DC current flowing through that wire. Well, that's the plan anyway. This obviously isn't calibrated, I'm just seeing the basic principle. So we're looking at about maybe 7 volts offset there. So it's a bit fiddly because this magnet's not ideal in terms of its north and south, but see if we can bring that in. Oh, there we go. Ooh. Yeah, so we can take all the way to 0 and back in. So depending on how much of that magnet it kind of sees, it can vary its position, and we can get it quite low. So that one is about 1 volt there, all the way up to 7 volts, depending on the level of magnetic field, which is generated by the clamp ultimately, which is generated by the DC current going through that wire that goes through that clamp. Right. Okay, we're getting somewhere. I think what we need to do now is make this special clamp that's got the Hall effect sensor built in. So let's go and do that, and then I'll show you that. Obviously when it goes together it's like that, and it's picking up the AC current of whatever goes through here, detecting it on there, inducing a current, and then so those two, they're probably the resistors for the burden resistor. I don't know what that is, maybe it's a diode, not sure. And then the voltage comes out here proportional to the current. Obviously we don't need any of that, and it looks like that has been moulded onto there. Right, well, the grinding was going okay, freehand, but you can see that made a very neat job of it. So probably need some kind of fixture to make sure I only grind so far. But a big problem on that when it was in the vise, there was a click noise and it snapped in half. And for now I might be able to screw this back together, but I've already really gone probably a bit too far on that, because it's a bit hard to see what you're doing because you're grinding blind. Right, anyway, the other thing I've decided to do is take apart the core just to get the other one out. Maybe you can buy these individually, these C shapes, and I could buy a load. Should be load cheaper, and then I can practice a bit more and get something set up. But anyway, that's what's happened. And you can see over here I've decided, because I don't need any of this, just to take the core out. There we go. Just left with that bit. I just wonder if it's worth carrying on trying to, because this is proof of concept after all, maybe glue that back together. See if my little Hall sensor will fit in there, epoxy that together, epoxy the whole thing together. Because all I want to do is just, if this works, I'll just put a wire through, I won't have it clamping round. If that works, I can move on to having it clamped around. Yeah, I think that's what we'll do. Right, let's get the epoxy out and glue it together. Okay, I've just soldered on some cables there so I can plug it back into the circuit board, and then super glued this back together. Turns out super glue seems to work really well on this iron material. It's pretty strong. It's not the best repair ever, but hopefully it's a proof of concept again. There's our little Hall effect sensor glued in there. So we'll just pass the cable through, measure some current, and just see what happens. Right, let's take this inside, hook it up, see if it works. So we've got our CT Hall effect clamp there running through this loop here. I've got a high power resistor there so we can put a lot of current through. It does get a bit warm, but it's within its rated capability. And then I can check the amps here. I can also see the amps that I've got set on there, and I can see how the amps vary as it goes into the Arduino, into the analog in. And then I've got a digital port coming out, and this is only an Uno, so it's putting PWM pulses out. So let me show you what you get when you play around with this on the oscilloscope and on the multimeter. Okay, I've moved them so they're both in the shot now, so this is how many amps we're going to put in, and then that's the milliamps are coming out of our detection circuit. Remember, this is doing the RMS of that PWM signal. Oh, it's DC, that won't help. Alright, let's try it. AC. Right, we're measuring current on there. Okay, well, let's go. Let's see if we can get about 1 amp. Okay, so we've got 1 amp coming through the coil, and we've got 3 milliamps there. Let's get 2 amps going through it. Somewhere there. 2, and it's 6-ish, 6 and a bit, so that's not too bad. I don't know if we'll get to 4 amps. It's going to start to get a bit warm. It is rated at 50 watts, but it does seem to get hot before then. 4. I think 4 amps. Oh, that is going to get very hot, yeah. In fact, it's limited on current. 4 amps, maybe 13. Okay, you get the idea anyway. Okay, exactly the same setup, except I've now got the output connected up to my scope over there, and so I don't block your view, I'll just try and turn the volts up. Put more current through that circuit, and we should get some. There we go. See how low we can go. So we're getting some PWM signals out there. So how they work is, in a given set of time, how often is it on compared to how often is it off. So if it's barely on at all, that's a very low signal as an RMS, like integration under the area under that curve, if you like. And then when you've got lots of pulses, so if I turn this up, see the current goes up and the pulses basically become solid. Pretty much on all the time, so they vary according to the current here. It's going through the main loop, so great. We're getting the PWM out and then the multimeter, or I'm hoping the Harvi will be fooled into thinking this is a number of milliamps going through it, and it will vary the kilowatts setting that it thinks it will reading that it's giving out. That's the idea. So I think we are a step closer. So you might think we're pretty much there. All we've got to do is calibrate the Arduino, so we've got the 0 all set and the amount of gain, and get it all tidied up, and basically put it into the cabinet, hook it up to the Harvi, and then it should appear on the app, right? Well, no, it turns out it's not quite that simple. So I did try this last night, and I had that signal going into the Harvi, and just the PWM signal, and I got an error on the app. A little yellow triangle came up, and the warning was something like it detected another generator potentially was on the network, and you needed to configure it and install it and follow this link. I think what was basically happening was I was injecting the current as a kind of sine wave or pulses in there, and that wasn't necessarily in sync or in good timing with the voltage that it was detecting through the primary CT or its own internal circuitry, because it's linked up to the mains, to the grid, and that it knows what the voltage signal should be, and I was putting a random current signal that could have been at any phase relationship to that, and it obviously thought that was another generator. So it was a good sign, it's an encouraging sign. It kind of says maybe I can get this to work, but I've still got a little bit more fooling to do. Now you might have seen these down here. I just ordered these are little amplifiers, I think they're basic audio amplifiers, just in case, because there's no digital to analog converters on the Arduinos. You have to have or the Uno hasn't got one anyway, so I need the external digital to audio, digital to analog, converters, and that is to convert the PWM signal into a nice smooth sine wave. Now there might be a bit of latency with that, I don't know, we'll see, but at 50 Hertz hopefully it's pretty trivial and it will still work. That's just in case the Harvi needed a proper analog signal, because that's what it's going to be getting from the sensor, the original CT clamp, the AC one. So I've got that in just in case it needs that, but clearly we need to have it phase referenced. The sine wave of the amps that I'm putting in, the milliamps, needs to be phase referenced to the voltage or within a very small degree, and I think so because it's going to use inductive probes, it would expect the current to lag the voltage very slightly, maybe half a degree or something like that, and if it sees that, it probably then goes, okay, the voltage or the power is going one way, and it will say the power's coming out of the battery or whatever, out of the panels. And if it sees that it's leading, because it knows it's an inductive sensor and that can't happen, it must be going the wrong way or the other way, and it will say, oh, the power's flowing the other way. So I suspect that's how it's doing it, but it will need the current and voltage to be pretty close to each other, so it can multiply them together at least to get the power. If they're a long way apart, that calculation won't work, or you get this horrendous power correction factor that's all wrong. And I suspect it was seeing that was too far out of phase, so I need to phase lock it onto the voltage and generate the sine wave that according to that. Now that sounds like a nightmare, but actually I think there's an opportunity here to simplify the whole thing. So let me draw it out as a block diagram and think of all the stages I need, or at least I want to consider, and then we'll see how many of those are actually required, or if there's yet more to be discovered. So what have we learned? Well, we had a look at these CT clamps, both the voltage type and the current type, and realised obviously they're only for AC. So we then went and made a custom Hall effect sensor to measure DC. We tested that out and validated it does actually work. Also then learned that the Harvi, it clearly needs much more than just a simple PWM signal. It needs something that's phase locked with the mains voltage, or 180 degrees out of phase if it needs to indicate the direction is actually reversed. So progress, but more to do. Next time we'll try to generate a current sine wave which is actually phase locked to the voltage, and we'll discover that the LM386 amplifier and the DAC unit I was using didn't really work as I expected. We'll also get something hooked up to the Harvi and realise that that does not work either. So I then flick through my notes for inspiration, and then I build a completely different circuit, and this happens. Yes, finally, after probably, there must be 4 or 5 weeks of work, 50 hours plus, trying every every way to get this thing to work. It finally works. I've got a proof of concept.